Thank you for coming, guys. My name is George, and today I'm going to present and talk about recommendation system which we recently built on one of our projects. Um, so a few words about me. I'm big data engineer in Green Dynamics company. I'm like Scala and I love Spark framework, and luckily we've got a lot of related projects, so I have an opportunity to use that on production and lot. And last 2 years I'm working with recommendations as a data engineer for one retail company, and I want to share some experience. Okay, just a few comments that I have a pretty straightforward material, so it should be pretty understandable. And the second thing that I would present the problem from engineering perspective. So I'm going to omit some data scientist aspects just because I'm not a data scientist. So anyway, this is our plan. So for the beginning, I'm going to overview some popular recommendation systems on the market. Then we will create the model which solve recommendation problem, and then I show you how we use the model in production and also show some demo. Okay, so I want to start with a little piece of motivation. Why do we talk about recommendation systems at all? So what's the matter? And the answer is a little bit cynical, but it's all about the money. People surprisingly bad in making choices. They don't know what we want until they saw it. And by providing some personalized recommendations, company may significantly increase their revenue. And that's why recommender systems become a pretty important business domain in the last decade. Moreover, recommendation systems are extremely widespread and take a part of our everyday life. And I want to show you a few examples of the systems which I often interact with. So let's start with a music domain. There are a few streaming services on the market right now, such as Spotify, YouTube Music, Apple Music, and some others. But speaking about recommendations, Spotify probably is the most advanced, and especially the playlist called Discovery Weekly, which is generate 30 new tracks every Monday for each user, and I'm a big fan of it. There are some information in the internet about the implementation of Discovery Weekly. So, long story short, that's just a collaboration of three different machine learning models. So the first model analyzes user behavior and feedback. So take a look at the picture. There are two persons with the same taste, so they can recommend something to each other. And this is the main idea of the first model. So the second model analyzes song text with natural language processing technique, and the third model analyzes raw audio with neural networks. So this is approximately how it looks like according to the information from the internet. So we've got a recommendation pipeline here which interacts with three models and involve different data sources and even Kafka with some real-time information, I guess. But our main interest now is batch CF model, which uses play logs and track metadata, because play logs, this is exactly what we call user feedback. So anyway, I don't know why all these tweets about comparing Discovery Weekly with a boyfriend, but it looks like people just go crazy for it. It's very popular. Okay, so the next example. It's game distribution services such as, for example, Steam. Unfortunately, there is not much information on the internet about how Steam recommendation system is implemented. Just one blog post from 2017, and it says that Steam uses two different approaches. So the first approach analyze user behavior and feedback, and the second analyze the information provided by game developers. And it's pretty enjoying how Steam explain why the stuff was recommended. So it sounds like, don't be mad on me, I recommend that for some reasons, and there are these reasons. I mean, it's cool. Okay, so let's move on. The next example is YouTube. I'm kind of ashamed to put here my personal YouTube recommendation, so that's just a random image from the internet. So when I'm thinking about the YouTube recommendations algorithm, something like this really comes to mind, because it seems pretty random sometimes, and luckily I'm not the only one who thinks so. I pretty common needs the comments like this. People just got frustrated why this is recommended and why like this disposita again. But I think that building recommendation systems as YouTube is quite complicated task, because you've got a million of users and billions of videos, and actually Google posted a paper on the internet with explanation how recommendation system works. So in a nutshell, this is a collaboration of two neural networks based on TensorFlow. So the first network, called candidate generation, it analyzes user behavior and feedback, and it provide hundreds of candidates for a second network called ranking. So ranking uses some additional information about videos and finally computes the actual results which user see on its screen. And yeah, it looks like pretty complicated system. Okay, so the next example is Netflix. Netflix recommendation system isn't like the single algorithm, but rather a set of different models which serving different use cases, such as personalization, because you watch, trending now, popular now, continue watching, and so on. So there is something in common between all these examples, one way or another, but all of them analyzes user behavior and feedback. And this kind of recommendation systems called collaborative filtering. And collaborative filtering includes two types of recommendations. So the first type, called personalized recommendations. So what does Netflix know about me? Just my likes, dislikes, what I was watching, which movies I added to my list. But still, using this information, Netflix able to provide personal recommendations that works exclusively for me. And the second type is similar items, or what called on Netflix because you watched. Using the same information, Netflix can analyze how similar different movies make impression on user feedback. So this kind of similarity between movies. And these two types of recommendations, this is pretty similar to what we have built on our project. And now I show you the model. Just for better understanding, I will use movies domain instead of retail. So there are actually a few types of recommendations, and collaborative filtering just one of them. There is also content-based systems which analyze discrete attributes and features of the product. But in reality, systems are more complicated than just collaborative filtering or content-based, and they have to use different approaches together, and this is kind of systems called hybrid. But in my talk, I will consider only collaborative filtering and the particular idea of implementation called matrix factorization. So anyway, what is collaborative filtering exactly? We have our users, products, and feedback, and we want to provide two types of recommendations, by user and by item. And the feedback itself can be two types. Explicit, that means user tells us his preferences directly, and implicit means that we make an assumption based on some information that we have. For example, what user purchased, what user added to bag, or like how many times the user spent on some page, and so on. And in reality, implicit feedback is more widespread because it's kind of complicated to get explicit feedback. People don't like to leave it so. And in general, collaborative filtering problems solved by construction user item matrix, which looks this way. So we have our products, users, and ratings, which we know. So now we can define a problem. If somehow we would able to estimate the empty cells, we would able to provide a good recommendation. So something like this. In this scenario, our recommendations would be a higher value and in estimated cells. Oh, sorry. And the problem of user item matrix that is just too sparse. In reality, we may have million of users and million of items, and only low number of users provide feedback on a few products. And it's just too complicated to do math with this representation, and that's why many ideas and approaches try to evolve to some dense representation instead of. And matrix factorization is one of these approaches. So the idea itself is pretty simple. We want to represent a big single matrix as a multiplication of two lower matrices. So in order to do that, we have to introduce new variable called factor. So this is an example how we combine 4 to 4 matrix as multiplication of two matrices 4 by 2 and 2 by 4. And I want to explain the factor idea on particular example. So if we define factors as a movie genres, we can create two matrices, one for users and one for items. And item matrix shows how each movie corresponds to each genre, and the user matrix shows how much user loves each genre. And for example, Pirates of Caribbean might be a good action, adventure, and a fantasy, but probably not so good as a family film. And we probably want to recommend it to Stacy because she likes actions and fantasies, or for example to John because he likes action and adventure. But we definitely would not recommend it to Rob, who likes families, films. So this is the basic idea how it works. So eventually, using this approach, we can reconstruct any empty cell from initial user item matrix. So for example, if we want to find out an answer how Stacy would like product C, we just need to make a multiplication of vector of Stacy from user matrix and vector of product C from the item matrix. And that's it. So now we've got two questions. So how we would define factors in our production system and how we would make factorization, because we can hire 100 analysts who would do that for us, but this is just like too expensive. And luckily, there is algorithm called alternating least squares, which do exactly this job. So we just need to provide number of factors, and it will have like factorization for us. So I want to leave technical details behind, but in a nutshell, we just construct lost function by ratings, which we know, and then iteratively minimize it. And important detail here that the factors provided by ALS, they have no interpretation or representation or like explanation. So that just a number, some mathematical abstraction. So don't try to understand it, you will fail. Okay, yes. So this is a high-level architecture of our application. We've got a model, which is just two matrices, and we've got two pipelines here. So the training pipeline, that's a process of getting model from input data, and the serving, that's a process of getting particular recommendations from a model. So in order to provide any recommendations, we need to implement two mathematical operations. So if you want to get recommendations for a user, we have to find user vector from user matrices. If we and if you want to provide recommendations by item, we need to find an item vector from item matrix. So then we need to multiply the vector by the whole item matrix because we want to understand how user or item correspond to any other items. And after that, we want to get like top 10 values from the result of multiplication, because from business perspective, you don't need a lot of recommendations, just like 10, 5, or 15 would be enough. Okay. So now let's consider implementation, how we did it. Before that, we actually need to think about the requirements, and there are a few important aspects. So the first one is how much data do we actually have. So this is our references point. We have around 9 million of users and 200,000 of items, and we've got implicit feedback, which takes about 50 gigabytes, and it updates every day, so we want to rebuild our model on a daily basis. The next aspect is performance. So we want to train our model within 3 hours, and we want to have recommendations, so doing these two mathematical operations within 100 milliseconds. So why it's important to have a good performance? Because in reality, we might have a chain of different models. So just let's consider the scenario that for some reason ALS is not able to provide any recommendations. In that case, we will translate the request to the second model, which would try to handle it. And if it's also failed to handle it, eventually it would go to some very generic model, for example, like popular now. That kind of model can provide recommendations for any item and any users. It would not be personalized, but anyway, it's better to show anything that return nothing. So each model should have a pretty good performance, otherwise UI would be waiting for a long time. Okay, so another aspect, that problems such as ALS pretty often solved by pre-calculation approach. So since our model is just two matrices, we can completely multiply it during training, do all this math, and get recommendations for all items and for all users, and then cache it in some key value storage, and that's it. We will have a really cool performance. But actually, we don't want to use this approach for two reasons. So the first reason, let's consider an example that we building recommendation system for some department store, where there might be some additional business rules, such as, for example, I want 5 brands to be presented across recommendation set, or I want all recommendations be within one category. For example, I want to see only dresses or shoes or hats in recommendations. And these business rules make the precomputation completely useless. And another point here, that this is one of the main advantages of the ALS algorithm, because it supports online learning. So instead of rebuild model on a daily basis, we can implement some kind of streaming and ingest new data and update our model in near real time. Unfortunately, we didn't implement this yet, but like this is our plans for the next year. I mean, for this year. Anyway, ALS is quite popular algorithm. There are a lot of implementations on different languages, machine learning frameworks, and one of the most popular implementations in Spark mlib framework. Okay, so this is approximately how looks like our training pipeline. So We've got three stages here: the ETL, the training itself, and preparation. All these stages implemented as Spark applications, and there are also some after each stage we save the data on HDFS or Google Bucket. So let me explain the meaning of all these stages. So why do we need ETL? And in this stage we want to clear the data. We want to filter out the information which can hurt our model. For example, we want to filter out the users which has just too less information, or again, if we making recommendation system for a department store, there might be a smaller retailers which can, you know, just buy everything in our system and then try to sell it on their side. This kind of information is hurt our model and we want to filter out. Also on this stage, we try to handle cold start problem. This problem appears when you got new products in a catalog and there is just no information to provide any recommendations for them. That's not a cool way to handle it, but we just filter out such products and we hope that the next model can provide something for them. Okay, so the next stage, the training model itself, and I want to show you the main parameters of the Spark implementation or how to use it. So we just need to define num blocks. This is a parallelization level, so we want to split our model on some blocks and handle them in some parallel manner. The next parameter, rank, this is just a number of factors. And max iteration, this is how much iteration ALS algorithm should do to minimize the cost function. So rank and max iteration, this is kind of compromise between accuracy and performance. So we can define more factors and more iteration, so we will improve accuracy, but we need more power to handle it. The next rec param, this is a regularization. So how much like numbers should be in our model? Would it be millions, or it would be just a small numbers between 0 and 1? So that's a regularization. And final parameter, we would define like what our input data, is that implicit feedback or explicit feedback? And that's it. And after that, the preparation stage. So once we train our model, how are we supposed to get good performance? So we decided to put user metrics as a key value into HBase or Bigtable. And the item metrics we just store in application memory as Java object, because we need the whole metrics to provide any recommendations for any item or any user, and that's just too expensive to store it in any storage. This is how much time it takes. So we can play around with ALS parameters and make the training time more or less like. Okay, let's move on. And now let's consider serving. So the main feature of our serving is usage of Breeze library. That's pretty popular library. That's a wrapper for a native library called Bless. And this library used by Spark itself for some mathematical operations. This is benchmarks made by GMH. So in our scenario for 200,000 products and 50 factors, we make multiplication just in 7 milliseconds and multiplication and get top key in 70 milliseconds. That means we have some space here. For example, we can increase the number of factors because 70 is like much less than 100, which is our requirement. But anyway, this is how the heart of our application looks like, the object called scorer. So this method top key is responsible for recommendations calculation, and it takes a vector, so that would be like user vector or item vector, and number of recommendations which we want to return. And this is our recommendation. So recommendations, that's just a product ID and a score. So in order to get recommendations, we need to multiply the matrix by a vector. So that's a breeze objects. And after that, just get top and elements from the multiplication result. I think that arctop key probably works with data structure called heap, so it returns unsorted elements, and we want to sort it to show more relevant. Okay. This is a schema of our serving. So we have a web server, and this is how query looks like. So this is like user ID and number of recommendations. And we just need to go to the storage to get the vector by user ID and then call the scorer object, and that's it. The same situation for item, but we don't need to go anywhere because the item vector already inside scorer. Okay, anyway, now I want to show you how we can implement, for example, like business rules based on this architecture. So what if we want like to have at least 5 different categories to be presented in recommendations, or otherwise like just all recommendations within one category? So in this scenario, we want to split the item matrix into smaller matrices grouped by a category. So all the products within same category would be grouped into the same matrix. And in that scenario, each category or each group will have its own scorer object. So now we have a query like this, so that a list of categories that should be involved in recommendations. And this is like number of products per each category. And we just have an iteration across categories and call the scorer object from each category and then combine the results together. So like pretty simple. Anyway, this is our technology landscape. So all the modules implemented by Scala, or in rare occasions with Python. And we use Akai HTTP for web part. From infrastructure perspective, we use Google Cloud, and we have Kubernetes clusters. So all the modules shipped as Docker containers, and we also use Argo pipelines for some synchronization. Okay, so that's it what I wanted to tell, but now I want to show a demo how it looks like. For a demo, I took a free data from Movie Lens. That's analysis which were collecting dates from 1996 to 2018, and it has 600 users and 10,000 movies. Yeah, and each user has at least 20 ratings. Okay, so let me show you. Okay, I have a few examples here already, so let's see the user which ID is it looks fine? Can you see it? Yep. Not so good. Okay. Better? Okay, let's try to do this. So we have our user with ID 9, and this is a history of the user, but I showing just the movies which user actually likes. So that's 5 with 5 rating or 4.5. So like user like this. So we can see here Indiana Jones, Back to Future, Lord of the Rings, and all that stuff. And this is how recommendations looks like for this user. And it's pretty remarkable that we see here Lord of the Rings and Indiana Jones, because from algorithm actually doesn't know these films are related. It doesn't know that Lord of the Rings is the same series. For the algorithm, that's completely different. And that means basically that users tend to put the same ratings for each movie from a series. So if people like Lord of the Rings, it like all 3 movies. Or if it like hates Lord of the Rings, it hates the same like all the movies. And the next example, like some user 244, where it's like Heat, Braveheart, Maverick, Forrest Gump, and some other films. And this is how recommendations looks like. It's not always reasonable, but sometimes you can understand, and sometimes it like there is no explanation why it looks this way. And this is how similar items looks like. So this is the Hop, some animation movie, and it tends to recommend animations movie for the animation. So it makes sense, I guess. And the recommendations for Interstellar. I mean, Interstellar is about the space, and there is like some other space movies like Star Wars. And anyway, there is opportunity to see the results for a pretty random user, for example. Does it work? Yeah. So some random user, this is his history, and this is how recommendations looks like. Again, the Rock, Star Wars, Forrest Gump, and well, anyway, how much time do I have? 10 minutes, okay. Okay, let's try to play a game. I have some prize here, but you need to imagine that you are like ALS algorithm. I would show you a history of a random user, and you just need to guess any film from recommendations. And the person who will guess the most relevant movie would get a prize. Okay? Well, we have time anyway. Okay, so let me show you a history of a random user. Okay, there is only 4 films that it user likes. It's a Wolf from Wall Street, Spider-Man, and Deathgasm. I don't know. I didn't. Okay, let's try another user. Okay, let's try this user. We've got Shawshank Redemption, Schindler's List, Lion King, Matrix, Green Mile. Yeah, it should be achievable. So you can just like guess any variant, and please do remember your guess. So anyone, please, just any guess. Which one? Green Mile already here in his. Blade Runner. Okay. Any other guess? Okay, The Shining. Godfather. Okay. Lord of the that's you're a cheater.
Why?
Because it's already here. Well. Okay. So okay, let's try see the results now. Okay. Brave, Star Wars. No? Okay, that was complicated. Let's try again. We have time still. It tends to recommend some popular movies from IMDb top or Kinopoisk top. So, okay, let's try this guy. We have Star Wars, Shawshank Redemption, Godfather, Toy Story, Forrest Gump, Casablanca, Citizen Kane, Mary Poppins. Okay, any guesses? There is no Green Mile. Okay, Green Mile. Okay. Any other guesses? Lord of the Rings. You're a cheater. Okay. Scary movie. Okay. 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 Let's try. Let's try. Brave. Toy Story again. Frozen. Avengers. Life is Beautiful. Does anyone have? No? Yeah, it's hard to be ALS. Okay. let the final try. We can make it. Okay, that seems to be complicated. Let's try other user. No. Die Hard, Superman, Star Trek, Harry Potter. Yeah, we can do this. Yeah. So what we have here, the Die Hard, Back to the Future, Shrek, Superman, Star Trek, Spider-Man, Jumanji, Aliens, Top Gun, Independence Day. So, any guesses? What? Interstellar, okay. Any other guess? Peter Pan, okay. Why not? Okay, that's it? Matt? You're a cheater. Okay. Star Wars, yeah, Harry Potter. Who was told the Star Wars? Okay, we've got a winner. Who was the first? Okay, I've got just only one prize. Yeah. Thank you. So that's it basically. Thank you for attention. And I think we have a time for questions. So are there any questions?
Thanks for your talk. I have a question. Basically, your algorithm implies that you do not count other users when you make a prediction for a particular user. So you don't have an algorithm like this user likes these films, that probably you also will like films like another user will like.
Yeah. So that's this information. I'll show you. This information took into account by ALS algorithm. So we don't use this directly, by algorithm use that in order to make factorization. Just because computers see something which people do not see. And that's just like ALS is like a one model, but we have some other models as well which use another type of algorithms and another structures and another information. Any other questions? Okay, it's lunchtime, so let's finish. Thank you.